On November 4th, 2025, a dashcam captured something terrifying at Louisville Muhammad Ali International Airport. Watch closely. That's a fully loaded UPS MD-11 freighter, moments after takeoff. The left side of the aircraft is on fire. Within seconds, it would roll inverted and slam into a distribution warehouse, killing all 3 crew members aboard and 11 people on the ground. 14 lives lost in total. What could bring down a modern wide-body jet like this? The answer lies buried in a crash that happened 46 years earlier, a regulatory failure that was never fully addressed, and a critical weakness hiding in the aircraft structure. This is the story of UPS Flight 2976. The afternoon shift at Louisville's cargo hub operates like clockwork. UPS freighters arrive, unload, reload, and launch across the globe. Flight 2976 was routine, a trans-Pacific cargo flight bound for Honolulu. The crew consisted of Captain Richard Wartenberg and First Officer Lee Truitt at the controls, with International Relief Officer Captain Dana Diamond in the cabin as a required crew member for the extended range operation. 3 experienced professionals, preparing for what should have been a standard flight. The MD-11 began its takeoff roll on runway 17R at approximately 5:13 p.m. local time. The aircraft accelerated normally, engines roaring at full takeoff thrust. But then, something went catastrophically wrong. Multiple cameras captured what happened next. The left engine, all 9,000 to 10,000 pounds of it, separated from the wing. Not a simple engine failure. Complete structural separation. The pylon, the massive structure connecting the engine to the wing, had torn free. Fire erupted immediately from the damaged wing. Fuel and hydraulic fluids sprayed into the evening air. The aircraft continued down the runway. Rotation occurred, and the pilots lifted off. They had no choice. They'd passed V1, the point of no return. So how does a modern wide-body jet, designed with redundant systems and built to withstand extreme forces, tear itself apart on departure? The answer requires understanding one of aviation's most dangerous failure modes. Let's break down what happened, second by second. The engine separation occurred during the takeoff roll. Video evidence shows flames visible from the left wing almost immediately, meaning hydraulic lines and fuel systems were breached the moment the pylon tore away. The pilots continued. They had to. Above V1 speed, attempting to stop would mean running off the runway at over 160 knots. The only option was to get airborne and try to control the aircraft. Rotation happened. The nose lifted. The main gear left the pavement. For a brief moment, it might have seemed survivable, but the MD-11 was already dying. The separated pylon had ripped through critical systems. Hydraulic pressure was dropping. The left wing, now structurally compromised and on fire, was producing asymmetric lift. The 2 remaining engines were creating a massive yawing force, twisting the aircraft toward the failed engine side. Approximately 25 seconds after rotation, the aircraft struck multiple structures, including a UPS distribution warehouse. The MD-11 was inverted or near inverted at impact. All 3 crew members died instantly. 11 people on the ground were killed, and 15 others were injured. The NTSB deployed a 28-person GO team within hours. Their investigation would eventually reveal something deeply troubling. Not just about this aircraft, but about an entire fleet. Investigators began with wreckage mapping. Every piece of debris was photographed, measured, and catalogued. The separated engine was found on the runway grass, its position revealing it had torn free during the ground roll, not after liftoff. The flight data recorder and cockpit voice recorder were recovered, despite the intense post-crash fire. The CVR captured the final 25 seconds, a repeating warning bell, the sound of the crew fighting for control, and then impact. The black box data showed something critical. Approximately 37 seconds before impact, multiple warning systems activated simultaneously. Engine failure alerts, fire warnings, hydraulic pressure loss. The flight crew faced a cascading emergency with no time to diagnose, no time to react. But the most important clue came from examining the wreckage itself. The investigation focused on one specific component, the aft engine mount. This is where the pylon attaches to the wing at the rear. This single connection point would become the center of the entire investigation. The NTSB's initial press briefing included key statements confirming what aviation observers had already suspected. This wasn't the first time a pylon had separated from this type of aircraft, and the parallels to an earlier disaster were impossible to ignore. May 25, 1979. Chicago O'Hare International Airport. American Airlines Flight 191, a DC-10, began its takeoff roll. Seconds after rotation, the left engine and pylons separated. The aircraft rolled inverted and crashed, killing all 271 people aboard and 2 people on the ground. 273 total fatalities in what remains America's deadliest aviation accident. The cause? Maintenance procedures that deviated from manufacturer specifications. American Airlines had developed a shortcut, using a forklift to remove the engine and pylon as a single unit, rather than detaching them separately. It saved time, it saved money, but it introduced forces the structure wasn't designed to handle. During one maintenance session, a forklift positioning error caused the pylon to contact the wing mounting bracket. The impact was barely noticeable. A few inches of misalignment, a brief moment of pressure. But it was enough to crack the pylon's aft bulkhead. That crack grew. Every takeoff and landing cycle, the fatigue crack advanced microscopically. 8 weeks later, during Flight 191's takeoff, the accumulated damage reached critical size. The aft mount failed. The pylon separated, but the engine separation was just the beginning. When the pylon tore away, it severed hydraulic lines running through the wing leading edge. The DC-10's leading edge slats, the devices that generate extra lift at low speeds, lost hydraulic pressure. Aerodynamic forces pushed them closed. With slats retracted on the left wing, the stall speed increased by 35 knots. Flight 191's takeoff speed was 153 knots, 6 knots below the new stall speed. The left wing stalled asymmetrically. The aircraft rolled. The pilots had no warning, no time, no control authority. The crash was unsurvivable. The NTSB investigation led to regulatory changes. Hydraulic fuses were mandated. Slat relief valves were required to prevent uncommanded retraction. Maintenance procedures were supposed to be strictly controlled and audited. The MD-11, designed as the DC-10's successor, incorporated these safety improvements: hydraulic fuses in the tail engine system, enhanced cockpit displays, improved aerodynamic design. But here's what didn't change: the basic pylon attachment structure. The MD-11 retained the DC-10's fundamental design philosophy: 3 forward mounts, 1 aft mount. The pylon's 3 forward attachment points and single aft mount create a structure with no redundancy. If the aft mount fails completely, the entire engine assembly becomes unsupported. High-strength bolts connecting the pylon to the wing through precision-machined fittings. The same stress concentration points, the same single-point failure vulnerability. Investigators pulled the maintenance records for the accident aircraft. What they found is still under review. The MD-11 had recently undergone heavy maintenance, a D-check, the most comprehensive inspection an aircraft receives. The maintenance facility documented work on corrosion issues and a fuel tank crack repair. UPS indicated that no maintenance work was performed before the flight that would delay it in any way. But investigators are examining all recent maintenance activities for potential connections to the failure. Here's what we know from similar pylon attachment failures. They can develop between inspection intervals. A fatigue crack, initiating from a maintenance-induced defect, might grow from microscopic size to critical failure in just a few months of operations. The inspection procedures during D-checks include visual examination of pylon attachment bolts and fittings, magnetic particle inspection, and ultrasonic testing detect internal cracks. But these tests only work if the crack is large enough to detect, and if the inspector examines the exact location where the crack exists. A crack growing beneath a bolt head, inside the material where visual inspection can't reach, might remain hidden until it's too large to stop. The fracture mechanics are unforgiving. Fatigue crack growth follows Paris's law. Once initiated, cracks accelerate exponentially with each load cycle. For a cargo aircraft operating 6 to 8 sectors daily, a small crack introduced during maintenance could reach critical size in 10,000 to 20,000 load cycles. That's roughly 2 months of continuous operations. Takeoff is the most dangerous phase of flight. The aircraft is heavy, carrying maximum fuel and cargo. Engines operate at full power, producing maximum stress on all structural connections. Speed and altitude are minimal, meaning pilots have almost no margin for error. This is where V1 speed becomes critical. V1 is the decision speed. Below V1, pilots can reject the takeoff and stop on the remaining runway. Above V1, there isn't enough runway left to stop. The only option is to continue, get airborne, and deal with the emergency in flight. For a fully loaded MD-11 at Louisville that evening, V1 was approximately 160 knots or higher, meaning the pilots couldn't safely abort once the engine separation occurred. For the UPS crew, the engine separation likely occurred near or just after V1. Training emphasizes that above V1, you continue for an engine failure. The MD-11 is certified to climb safely on 2 engines. It's designed for this contingency. But this wasn't a simple engine failure. This was structural catastrophe. The separated pylon had torn through hydraulic systems, fuel lines, and possibly electrical systems. The left wing was on fire. Aerodynamic forces on the damaged wing were creating asymmetric lift. The 2 remaining engines, one on the right wing, one in the tail, created a massive yawing moment, roughly 1.4 million pound-feet, trying to rotate the aircraft toward the failed engine side. The pilots applied full rudder, trying to counteract the yaw. They banked right, trying to oppose the left roll tendency. But control authority was degrading. Hydraulic pressure loss reduced control surface effectiveness. The fire was weakening wing structures. The aircraft was approaching stall speed on the damaged left wing. At approximately 100 feet altitude, the left wing stalled. The roll accelerated. The aircraft inverted. Impact followed seconds later. Within hours of the crash, the FAA issued Emergency Airworthiness Directive 2025-23-51. Every MD-11 in service worldwide was grounded pending inspection. Approximately 70 MD-11 freighters operate globally, primarily with UPS, FedEx, and Western Global Airlines. These aircraft represent roughly 9% of UPS's fleet, but handle a disproportionate share of international cargo capacity, particularly trans-Pacific routes where large-capacity freighters are essential. The grounding created immediate supply chain disruption. Air cargo rates spiked by over 2%. Holiday shipping faced capacity shortages. The economic impact rippled through global commerce. Billions of dollars in losses across the aviation industry, shippers, and consumers. But here's the troubling reality. The emergency AD grounded the fleet, but initially left inspection protocols undefined, reflecting uncertainty about what structural defects to search for. The FAA didn't know what to look for. The root cause wasn't understood well enough to prescribe a fix. So what happened to UPS Flight 2976? The investigation continues, but the evidence points to a failure mode aviation thought it had solved 46 years ago. The parallels are striking. Both incidents involve pylon separation from the left side during takeoff, affecting identical structural systems that had been in production for decades. Both aircraft were trijets, with the same fundamental pylon attachment architecture, 3 forward mounts and 1 aft mount. Both resulted in immediate loss of control and fatalities. Both revealed that a single structural component, the aft pylon mount, represented a catastrophic single-point failure. The regulatory response to Flight 191 addressed the symptoms, hydraulic system vulnerabilities, slat retraction risks, but never fully addressed the root cause. Pylon attachment structures remained vulnerable to maintenance-induced damage, long-term corrosion, and fatigue crack growth that inspection procedures struggle to detect. The industry treated this as a process control problem. Follow manufacturer procedures, conduct inspections, report anomalies. But when maintenance technicians take shortcuts, when inspections miss hidden cracks, when economic pressures drive extended maintenance intervals, the system fails. The fundamental engineering flaw persists. The aft pylon mount has no alternative load path. If it fails, the engine separates. No redundancy, no fail-safe backup. The consequences are immediate and catastrophic. The NTSB investigation will eventually release a final report, detailing exactly what initiated the failure. Was it maintenance-induced damage, like Flight 191? Long-term corrosion that progressed beyond inspection thresholds? A material defect that existed since manufacturing? Whatever the proximate cause, the deeper failure is systemic. 46 years after Flight 191, we're investigating the same failure mode on the same basic structure. The lesson wasn't learned, the vulnerability wasn't eliminated, and 14 people paid the price. As of this video's publication, the NTSB investigation into UPS Flight 2976 remains ongoing. Final findings may reveal additional details about the root cause of the engine separation. The MD-11 fleet remains grounded as investigators search for answers. When or if these aircraft return to service, the question remains: has the fundamental pylon attachment vulnerability finally been addressed? Or are we still waiting for the next fatigue crack to reach critical size? The NTSB investigation is ongoing. As more information becomes available, we'll update this analysis. If you found this breakdown valuable, consider subscribing for future aviation accident investigations and analysis. Thanks for watching.